Hello everyone and welcome to Calc Lesson number 61. Today we are going to continue on with section 5.1. So we are still going to be looking at differentiation with the natural logarithm. In our last lesson, we looked at taking the derivative of the natural log of u, where u was a function of x. Today we're going to extend that a little bit further and look at taking the derivative with absolute value. Because the natural logarithm is undefined for negative numbers, you will often encounter expressions of the form the natural log of the absolute value of u. This theorem states that you can differentiate functions of the form y equals the natural log of the absolute value of u as though the absolute value notation was not present. So if u is a differentiable function of x such that u is not equal to 0, then the derivative with respect to x of the natural log of the absolute value of u is still just equal to u prime over u. So for our first example, we want to take the derivative of the function f of x equals the natural log of the absolute value of cosine of x. Remember from the previous slide that we can actually ignore the absolute value bars, and the derivative d dx of the natural log of the absolute value of u is still just equal to u prime over u, like we were doing in our last lesson. So I'm going to go ahead and identify my u as cosine of x. I'm going to take the derivative, so u prime, and remember my trig derivatives are on my formula sheet, so the derivative of cosine is negative sine of x. And I'm going to fill into my u prime over u definition. So my derivative f prime of x is going to be equal to negative sine of x over cosine of x. And luckily I know my identities, and I can rewrite this f prime of x as negative tangent of x. Okay, number 2, very similar. We're still taking the derivative. This one a little bit more exciting. Here our function is f of x equals the natural log of the absolute value of secant of x plus tangent of x. Remember, we can ignore those absolute value bars, and the derivative of the natural log of the absolute value of u is equal to u prime over u. Let's identify our inside of our function as our u. So let's let u equal secant of x plus tangent of x. When we take our derivative here, we're actually going to take the derivative of each piece. So u prime is equal to, using our derivative formula sheet, the derivative of secant of x is secant of x tangent of x. And then add the derivative of tangent, and the derivative of tangent of x is secant squared of x. Now that we've identified u and u prime, we can go ahead and find our derivative f prime of x by filling in our u prime over u. So this would be secant of x tangent of x plus secant squared of x all over our original u, which was secant of x plus tangent of x. Now I'm going to look at this function, and I'm actually going to simplify my numerator by taking a secant of x out. So this becomes secant of x, and I'm left with tangent of x plus secant of x over, and I'm going to write my secant of x plus tangent of x denominator flipped, so it's tangent of x plus secant of x, and we're allowed to do that because addition is commutative. Now I have the same factor in the numerator and the denominator, so I can cancel out this entire factor, tangent of x plus secant of x, in both the numerator and the denominator. And I can simplify my derivative f prime of x just down to secant of x. So the first two examples, pretty simple, taking the derivative with absolute value. Okay, so at this point, we're going to kind of transition, and we're going to go back to some of the other types of problems we did with derivatives, but now we're going to apply our new knowledge about the derivative of the natural log function. So let's start by finding the equation of the tangent line to the given graph at the given point. So hopefully you remember that the derivative is the slope of the tangent line at a certain point. So for number 3, the function we're being given is y equals the natural log of x to the 3/2 power, and we are looking for the line tangent to that graph at the point 1, 0. So the first thing we want to do is start by finding the derivative, then plug in our point to find the slope at that point, and then use that slope and that point to find the equation of the tangent line. So let's start by taking our derivative. Now, just like we did in our last class, we want to take the derivative of the natural log of x to the 3/2 power. And in order to do that, we need to actually start by first rewriting this. Using our properties of logarithms. So we're going to take this exponent and move it to the front. So I'm going to write my function as y equals 3/2 times the natural log of x. Now I can take my derivative, so my y prime, keeping my 3/2, this becomes 3/2 times the derivative of the natural log of x is just 1 over x, or y prime would be equal to 3 over 2x. Now remember, we are not just finding the derivative here, now we're actually finding the equation of the tangent line. So we have our derivative, and the derivative is going to help us find the slope of the tangent line. So let's go ahead and find the slope at the given point, which was 1, 0. So we want to evaluate our derivative y prime at the x value of 1. So plugging in, we get 3 over 2 times 1. So our slope, or our derivative evaluated at 1, is just 3/2. Now remember, the goal here is to actually write an equation of a line. So we know the equation of a line is y equals mx plus b. So let's start by plugging in the m, the slope that we know. So we have y equals, we found our slope to be 3/2 x plus b. And at this point, we need to find what our b value is by plugging in the point we were given, 1, 0. So we can plug in our 0 for y, keeping our 3/2 for m, and our 1 for x. We'll be able to solve for b. So we get 0 equals 3/2 plus b. So b will be equal to negative 3/2. So we can now write our final answer as an equation. So the equation of the tangent line to the given graph would be y equals, keeping our slope, 3/2 x minus 3/2. So a little TBT for you on the type of question, the finding the equation of the tangent line, and then of course applying our new knowledge of the derivative of the natural log function. Okay, the directions for number 4 are the same. We're still looking to find the equation of the tangent line to the given graph at the given point. This time though, our function is just a little bit more exciting. We have y equals 4 minus x squared minus the natural log of 1/2 x plus 1, and then the point we're looking at is 0, 4. We're going to follow the same steps we did in the last one, starting by finding the derivative. So I'm going to find y prime by taking the derivative of each piece. Remember, the derivative of 4, since 4 is a constant, is just 0. The derivative of negative 2, or the negative x squared, now I can use my basic power rule. I don't have to do a natural log here. Just bringing my 2 down, this becomes negative 2x. And then I'm going to subtract. Now the derivative of the natural log of 1/2 x plus 1, this is where I have to use the fact that d dx of the natural log of u is equal to u prime over u. In this case, our u would equal 1/2 x plus 1, and u prime, the derivative, would just be equal to 1/2. So this derivative is going to be u prime, which is 1/2, over 1/2 x plus 1. Now in the next line, I'm going to go ahead and simplify. So I'm going to actually keep this negative 2x, and let's go to the side here for a second and simplify. 1/2 divided by 1/2 x plus 1 is the same as 1/2 times 1 over 1/2 x plus 1. So if we think about distributing this 2 through, this would turn into 1 over 2 times 1/2 is just going to be 1x plus 2 times 1 would be 2. So we can go back, y prime is equal to negative 2x minus 1 over x plus 2. If I lost you on the simplifying, please feel free to pause the video and ask your teacher. Remember, when we're finding the equation of the tangent line, we don't need to do too much simplifying of our equation because we're going to end up plugging in anyway. So now that we have our derivative, let's go ahead and actually find the slope. And let's find the slope by plugging in our x value of our point. So we want to look at y prime of 0, which would be negative 2 times 0 minus 1 over 0 plus 2. So negative 2 times 0 goes away. So our derivative, our slope of the tangent line at 0, is just equal to negative 1/2. From there, we are looking to find the equation of the line, meaning we want to plug into y equals mx plus b. Start by plugging in that m. So we have y equals negative 1/2 x plus b. And then, of course, plug in our xy, 0, 4. So we have 4 equals negative 1/2 times our x value of 0 plus b, which just leaves us with 4 equals b. So we can write our final answer, the equation of the line tangent to the graph of y equals 4 minus x squared minus the natural log of 1/2 x plus 1 at the point 0, 4 is y equals negative 1/2 x plus 4. And again, if you have any questions, please feel free to pause the video and ask your teacher. Okay, for our last two problems, we are going to do another big throwback to a concept we were talking about way back when we started differentiation called implicit differentiation, which you may remember means that when you are differentiating with respect to x, if you are differentiating a different variable such as y, you need to account for it by using dy dx or whatever your variable is. So in this case, we're going to use implicit differentiation, and then we're actually going to solve to find what dy dx is equal to. So our problem number 5 is the natural log of xy plus 5x equals 30. Now our goal is to take the derivative, but you might recognize that what we have at first is the natural log of xy, which can actually be expanded. So let's start by taking the natural log of xy and using addition to separate that into two logarithms. So I can write this as the natural log of x plus the natural log of y plus 5x equals 30. Now that I've done this and I've separated out those logarithms, we can easily take the derivative of each individual piece. So let's take the derivative of the natural log of x, which we know is just 1 over x. When we take the derivative of the natural log of y, we know it's going to be 1 over y. But since we're taking the derivative with respect to x and y is not x, we need to account for dy dx. Then we can continue as normal. The derivative of 5x would just be a positive 5. Because the variable we have there is x, we don't have to worry about a dy dx. And the derivative of 30 is just 0. So now that we've differentiated each piece, our goal here is to actually solve for dy dx. So we want to get it all by itself. So let's start by moving our 1 over x and our positive 5 to the opposite side. So we have 1 over y equals a negative 1 over x minus 5. Oops, 1 over y dy dx. Now just to keep this nice and clean, I'm actually going to find a common denominator on my right-hand side by multiplying by x over x. So I have 1 over y dy dx equals negative 1 minus 5x over x. And to get y by itself, all I have to do is multiply both sides by y. And I'm just going to distribute my y through my numerator for my final answer. So we get dy dx is equal to negative y minus 5xy all over x. So hopefully implicit differentiation is coming back to you. The only new portion we're adding today is the fact that we can now apply the derivative of the natural logarithm. Okay, in the same directions for our final example, using implicit differentiation, let's find dy dx. Here our function is 4xy plus the natural log of x squared y equals 7. First thing I notice is this natural log of x squared y can be expanded and simplified. So I'm going to keep 4xy. I'm going to separate these and move my 2 to the front all in one step. So this becomes plus 2 natural log of x plus natural log of y equals 7. So feel free to pause here and go back and make sure you can expand that the same. Once we have our function expanded out, we can go ahead and take the derivative. Now don't get too excited or move too quickly, because here you have 4xy, and because you have x multiplying with y, in order to take this derivative, you actually have to use the product rule. So I'm going to take my two functions as 4x and y. Taking the derivative, it would be the first times the derivative of the second. So my first function would be 4x times the derivative of the second, which would be 1. Because it's a y, we need a dy dx, plus the second function, which is y, times the derivative of the first, which would be 4. And because it's an x, we don't need a dx dx or anything. Then we can continue with the rest of our differentiating. So when we differentiate 2 times the natural log of x, that positive 2 is a constant multiple that's going to stay. And remember, the derivative of the natural log of x is just 1 over x. When we take the derivative of the natural log of y, the derivative of the natural log of y is 1 over y, but because it's not an x, we need a dy dx. And then the derivative of 7, because it's a constant, is just equal to 0. So just double check your derivative. We have 4x dy dx plus 4y plus 2 times 1 over x plus 1 over y dy dx equals 0. So you probably remember from way back when you have a problem like this and you're trying to solve for dy dx, but you have multiple, you need to isolate your terms as dy dx so you can factor it out. So I'm just going to identify where my dy dx terms are, and I'm going to scooch everything else to the other side. So I'm going to keep, 4x dy dx, and I'm going to keep plus 1 over y dy dx on my left side. And I'm going to move my 4y's, this becomes negative 4y, and then minus 2 over x. And just like I did in the last problem, just to make it nice and clean, I'm going to multiply by x over x, so I have a common denominator. So this becomes 4x dy dx plus 1 over y dy dx equals negative 4xy minus 2 all over x. Now on the left-hand side, I have 2 dy dx terms. So remember, we can actually factor that out. So I'm going to jump up top here. On the left-hand side, pulling our dy dx out front, we're left with 4x plus 1 over y, and that is equal to negative 4xy minus 2 over x. And just like I did on the right-hand side, I'm just going to make a common denominator by multiplying by y over y. So we really have dy dx, and then we have 4xy plus 1 over y. And this is equal to negative 4xy minus 2 over x. And then in order to get dy dx by itself, we would just multiply by the reciprocal. So we get dy dx is equal to the original negative 4xy minus 2 over x times 4xy plus 1 over y. And just to kind of clean it up, we can actually multiply this out. Back it up, sorry. Multiply by the reciprocal, so this would be y over. 4xy plus 1. Sorry about that. Now we can multiply this out to clean it up. So we have dy dx is equal to, let's distribute our y and distribute our x. So we get negative 4xy squared minus 2y over 4x squared y plus x. So kind of messy, but also kind of fun, using implicit differentiation to get dy dx. Great job with these problems and with remembering all of those old rules from differentiation. Homeworks number 61 is on pages 325 to 326, and is number 61, 63, 65, 67, 73, and 75. Make sure you're checking your answers and ask your teacher if you have any questions.